Today we will discuss about indicators. As we know that a point comes which indicate the completion of reaction in the volumetric analysis, and that point is called equivalence point or end point. So equivalence point or end point is a volumetric analysis is detected by the addition of a suitable substance that changes its color when the reaction is just complete. So the suitable substance that changes its color when the reaction is complete is called indicators. And the indicator changes its color that is very close to the equivalence point and not exactly at the equivalence point. It is called the end point. Now we will discuss about what is now we will discuss about which types of substance used as indicators. Basically, as indicators we have used a weak acid or weak base. Most of the indicators are the organic compound. These are the organic compound which are either weak acid or weak base. Now we discuss the common example of the indicators. So if we have discussing the reaction between acid and base, then the common example of the indicators are that is phenolphthalein, and its shortcut becomes HPH, that is called phenolphthalein. And the second main indicator is called methyl orange, that is MEOH. It is called methyl orange. This phenolphthalein is it's a weak acidic indicator, and this methyl orange is a weak basic indicator. It means when we are performing a reaction between acid and base, so in the reaction between acid and base, there is no interference of the indicators. Some indicators are the weak acid or weak base. Now we will discuss about in details what happen when indicators indicate the completion of reaction, or how we can determine the end point or completion of the reaction by the help of indicators. So time to time there are different theories are proposed for changing the colors of the indicators. We will discuss about some common theories. So we will discuss first the theory, the most important common theory, that is called Ostwald theory. So theory becomes first stage Ostwald theory. Now, according to this theory, the color changing of the indicators due to their ionization process means indicators indicate their color upon indicator changes their color which are depend upon the ionization of the particular compound or particular compound which is used as an indicator. For example, if we are taking the example of phenolphthalein, It's a HPH, it's a shortcut notation for the phenolphthalein. Now, first we will discuss how we can prepare the phenolphthalein. Now, phenolphthalein is prepared by the reaction of phenol and phthalic anhydride. And the reaction is of this type. We are taking two molecules of phenol. This is the benzene ring. There is the alternate double bond and OH group. This one compound is called phenol. This is called phenol. We are taking another molecule of phenol and two molecules of phenol react with phthalic anhydride. Phthalic anhydride means this types of, here is the benzene ring. We can also draw a circle in place of alternate double bond. So this compound becomes called phthalic anhydride. This compound is a phthalic anhydride. After the reaction, we will obtain a phenolphthalein, but the reaction performed in presence of concentrated esters of 4. And after the reaction, we will get, here is the H, here is the also H. Now this oxygen from phthalic anhydride and this hydrogen from this phenol and this hydrogen from this phenol. So these two hydrogen and oxygen form H2O, and after the removal of this H2O, the structure is this type. We will draw a circle in place of alternate double bond. Now another benzene ring, drawing a circle. Here is the OH group, and the removal of two hydrogen, these two rings joining with the carbon. This carbon comes from phthalic anhydride, and this is the phthalic anhydride ring. This ring, and carbon join this. Here is the C double bond O, and here is the CO by the removal of H2O. Now this whole structure is called phenolphthalein. It's a phenolphthalein molecule, HPH. Now in this structure we are having this one benzene ring, this one benzene ring, and this one benzene ring. So this one structure is called benzenoid structure of the phenolphthalein, and this type of structure exists in its neutral or acidic solution. And when phenolphthalein exists in neutral or acidic solution, then structure of these types and these types of structure becomes colorless when we are using phenolphthalein in basic solution. Now see what happened. This one is the phenolphthalein molecule. Here is the benzene ring, that is the alternate double bond. Here is the OH group, and another molecule of phenolphthalein with the OH group joining with the carbon comes from phthalic anhydride. There is the ring of phthalic anhydride. This one is the phthalic anhydride. This one join this. Here is the C double bond O, and here is the O. So this one is the phthalic anhydride, and the whole structure is called phenolphthalein. And in this form we are having 3 benzenoid rings, and at this time phenolphthalein is colorless. So this types of structure exists in its acidic or neutral solution. When we are adding basic solution, that is NaOH, sodium hydroxide, or any basic substance, and what happens if we are adding NaOH, then OH minus, which comes from NaOH, react with this phenolphthalein, and these types of, in the phenolphthalein, these two hydrogen are called acidic hydrogen. So this H plus combine with this OH negative and gives a H2O. After removal this H2O, you will find a negative charge on this oxygen atom, and this negative charge is resonance stabilized with a benzene ring. So the pattern of this type, this one is the benzene ring. After removal of H2O, you will find a negative charge, and negative charge is this types of resonance stabilized comes in this rank. When negative charge comes in this point, then this point shifted to in this position, and when this point shifted to in this position, then this bond directed to that side, and when that side, then this bond is already bonded with carbon bond is turned off this side, and remaining structure of intact is this type. There is no change in the remaining structure. It's CO, C double bond O, here this, and this side becomes another benzene ring having OH group, and this carbon bonded with this. So if we are writing down this structure, then we are having this types of structure. This ring, Yes, having double bond oxygen, and here is the one double bond, here is the double bond, here is the double bond, here is the double bond that bonded with the C. Now this one side the structure remains intact, so this type is the C double bond O, and here is the negative charge comes on oxygen atom and ring is break up. Now this side, the ring pattern of this one is, here is the OH. So when we are adding NaOH or any base in the phenolphthalein, then structure turns to this. In this structure, we have seen that there are two benzene rings, but this one is the another ring. This one is the another ring, and that ring is called the quinoid ring. That ring is called quinoid ring. And due to the presence of this quinoid ring, phenol gives its pink color. So in basic medium, due to the presence of this quinoid ring, phenol gives pink color. And if we are taking the Arrhenius concept, then according to Arrhenius, there is a different form, there is a different colors in ionized and non-ionized form. For example, if we are taking the example of phenolphthalein, HPH, it is the non-ionized form. Upon ionization, it gives H plus and pH negative. That this pH negative is called anion of phenolphthalein, which we have already discussed. And this pH negative becomes pink color. It's a pink color. When we are taking the acidic solution or in presence of acid of the phenolphthalein, then for example, if we are taking the HCl, and HCl gives H plus Cl negative ion. So H plus ion obtained from both sides, that is from phenolphthalein and from HCl. So when we are applying law of mass action on this phenolphthalein reaction or reaction first, then we are getting that in the phenolphthalein reaction, equilibrium constant, that is K, becomes H plus pH negative upon HPH. In this reaction, concentration of H plus increased due to the common ion effect of H plus. Is this type? So since H plus obtained from two sides, that is from HCl and from HPH. So in this reaction, concentration of the H plus is increased. So for controlling the value of K, here is the HPH. In the HPH reaction, the reaction shifted towards back side, means that is unionized side. Means H plus and pH negative, which is ionized, further combined with and gives non-ionized HPH. So H plus concentration becomes decreased, and if H plus concentration becomes decreased, then automatically concentration of the pH negative also decreases. Means ionized phenolphthalein converted into non-ionized HPH. So in acidic medium or in the neutral medium, phenolphthalein becomes colorless. So acidic medium or neutral medium, phenolphthalein becomes colorless. But when we are taking basic medium, then what happens? If we are taking NaOH in place of HCl, NaOH is a colorless, it is ionized and give Na plus OH negative. Now OH negative, which is obtained from NaOH, is combined with the H plus, which is obtained from phenolphthalein, and this H plus and OH negative form H2O, which is almost non-ionized. So if we are adding NaOH, then in this reaction we are getting the less concentration of H plus, since H plus which will be obtained from HPH combined with this OH negative, which will be obtained from NaOH, and form a non-ionized H2O. So here is the concentration of H plus is decreased. Now for controlling the value of K, here is the HPH, which more ionized and gives more H plus and more pH negative ions. Means in the basic solution, we are getting more H plus and more pH negative ions. Due to this more pH negative ions, phenol becomes pink color in the basic solution. So in basic solution or in basic medium, HPH having pink color due to pH negative ions. So indicators play their role which are depend upon the color changing process, and their color changing process depend upon their ions which we are getting from their ionization process or which we are getting the resonance process. And when we are taking the resonance in the phenobenzene, then we are getting when it is having benzenoid structure, means benzening type of structure. This one types of structure, this one is called benzenoid structure. Benzenoid structure, it becomes a colorless. But when we are having this types of ring, that is called Cunard ring. It's a colorful. So this is the common theory which are depend upon resonance or Arrhenius concept. Now we are discussing about self-indicator. Self-indicators means what is the meaning of self-indicators? So self-indicators means when our substance that we are using in the titration act as indicators, then it is called self-indicators. For example, if we are performing the titration or reaction between KMnO4, that is potassium permanganate, and ferrous ammonium sulfate, that is FeSO4 dot NH4 whole twice SO4 dot 6H2O. This is also called Mohr salt. So when we are performing the reaction between these, then in this reaction or in this titration, the reagent KMnO4, that is also called oxidizing agent, the KMnO4 act as a self-indicator in this titration. Actually what happens? The color of the KMnO4 becomes dark violet. KMnO4, it's a dark violet substance. So when we are performing the titration, then initially when we are starting the titration, then the color of KMnO4 becomes violet, and after the completion of reaction, basically this KMnO4 converted into Mn plus 2, and this Mn plus 2 almost colorless. Mn plus 2 becomes colorless. So when we have completing the reaction of this KMnO4 and ferrous ammonium sulfate, then when equivalence point comes, then the whole KMnO4 react with ferrous ammonium sulfate converted into Mn plus 2, and Mn plus 2 becomes colorless, so the color becomes decolorized. But as soon as the reaction between KMnO4 and ferrous ammonium sulfate is completed, and after the completion of reaction, we are adding even single drop of KMnO4, then the drop is of the KMnO4, and due to this last drop of KMnO4, the color of the whole solution is pink color, that is light pink color. So this light pink color indicates that our reaction is complete. Since initially the KMnO4 it looks violet, since here is the concentration of the KMnO4 is more, but at the completion of reaction it looks pink color, since when we have completed the reaction, then we have a colorless solution about 20 to 30 ml, and when 20 to 30 ml solution, when we are adding only single drop of KMnO4, then due to this single drop of KMnO4, the color is violet is not appear, the color becomes appear pink color. So pink color of the KMnO4 appears when its concentration is very dilute or when KMnO4 is used in the very dilute solution. So in this titration, the KMnO4 acts as a oxidizing agent as well as indicators. So these types of indicators is called self-indicators. If we are using potassium dichromate, that is orange in color, K2Cr2O7, it is orange in color. If we are using this potassium dichromate in this titration, then potassium dichromate is also a strong oxidizing agent, but it is not act as a self-indicator since potassium dichromate having a orange color, but its color is not so intense. But in case of KMnO4, it is a good oxidizing agent, but its color is very intense. Therefore, it's only single drop to indicate the light pink color. So that's why we are using KMnO4 as a self-indicator, but we are not using potassium dichromate as a self-indicator. If we are taking the titration or reaction with the potassium dichromate, then we are using a external indicator for detection the endpoint.